Hello students, this is a brief lesson on the first law of thermodynamics. So we're going to call this lesson 2 in chapter 6, thermochemistry. The first law of thermodynamics tells us that the energy of the universe is constant. We know that energy is conserved. However, this just is a different wording for us. Whenever we are taking a look at really the energy exchange within a reaction, we're looking at the internal energy of our system. We can change the internal energy of the system by changing Q, heat, or work, either by having the system do work on the surroundings or the surroundings do work on the system. Now, there are two main things that we need to just make sure that we really focus upon for every thermodynamic term. Every thermodynamic term has a value or a quantity, the size of the number, and a sign either being positive or negative. So, the sign of the thermodynamic term indicates the point of view. And we are always trying to be in the point of view of the system. So, if we're looking at heat, so we said, if the heat is negative Q from the perspective of the system is losing heat. So that would be exothermic. Where if Q is positive, the system is gaining heat, so it's endothermic. Well, what about work? Well, if work is positive, then that means the surroundings did work on the system. The surroundings did work on the system, so the system gained work. Where if it's negative, that means the system lost work, giving it to the surroundings. Okay, we'll come back to this. So mathematically, the first law of thermodynamics can be referenced as delta E, which the change in internal energy we're going to call capital E, or just our energy of our system, is equal to Q plus W. Now, usually, as far as chemistry goes, we're doing reactions in open containers. And we need to be able to seal the container to really be able to see work from our system or to our system. Your book does a beautiful, beautiful derivation. But if we go back to how can we get work out of a chemical reaction, we need a system with a piston. So this image here is showing us a vessel with one of those movable walls. If we can change the volume within our system, if we can change within the volume of our system, then that is accomplishing work. So a change in volume, as far as a reaction is concerned, to the vessel, that will accomplish work. Now, we said work is force per unit distance. Well, and your book does a beautiful job of this, showing you the derivation through this kind of an image. Work, according to a system, will be pressure change in volume, where pressure is an outside pressure that is being exerted on the piston. If this is our system, if the vessel undergoes a change in volume, if it expands, if it pushes against the outside pressure, and you end up with a positive change in volume, well, the work has been lost by the system. The system caused that change in volume against that outside pressure. So that would be negative work. However, if the piston was pushed downward, if we had a decrease in volume, then the system was worked upon. The surroundings did work on the system, and work is positive. So if you have expansion, our change in volume is positive, then work is negative. If the surroundings did work on the system and you had a decrease in volume, so you ended up at a smaller integer than you started with, then, according to the system, work was done upon it. I like to just look at work as P delta V. However, Zumdahl says if we want to attach a negative sign, and then if we're expanding or contracting, then work will automatically be positive or negative, and then we don't have to worry about thinking about our sign. But I would rather be of the perspective that we always look at our value and assign the sign per our system or surroundings. It is totally up to you. So, if we want to just dig into one quick example, calculate the change in energy for a system undergoing an endothermic process in which 15.6 kilojoules of heat, so Q, 15.6 kilojoules, it's endothermic. So this is coming from the surroundings. My system is gaining, so it's going to be positive. Where 1.4 kilojoules of work is done on the system. Work is 1.4 kilojoules done on the system, so the system gains the work. Delta E is Q plus W, making sure that they're the same unit, making sure I have the signs correct. Then 15.6 kilojoules plus my 1.4 kilojoules gives me, with sig figs, 17.0 kilojoules as my change in energy. Okay, now doing an example of this equation, and again, depending upon if you want to think about attaching the sign or not. Calculate the work associated with the expansion of my gas to 64 liters from 46 liters at a constant external pressure of 15 atm. I know that work is P delta V. 15 atm, I've undergone expansion. So what I'm going to get up as my answer is 270 liters times atmosphere, or atmosphere times liter. Now usually write it liter atmosphere because that's how you'll most commonly see it in your textbook. Now, expansion. The system did the work to increase the volume, so it lost work to the surroundings, so work is negative. But what on earth is a liter atmosphere? We usually see work in joules. Well, for every 1 liter atmosphere, it equals 101.3 joules. So we can convert liter atmosphere to 101.3 joules, and we get a negative 27,000 joules, or negative 27 kilojoules. Now, we may also be asked to interpret work, the sign of work, based upon just your reaction. So, if we take a look at solid sodium reacting with chlorine gas to create solid sodium chloride, if you're asked to predict the sign on work per your chemical reaction, we need to compare the moles of gas of reactant to the moles of gas of product. Here we only have 1 mole of gaseous reactant and 0 moles of gaseous product. So if we look at how will our volume change, we go from having gas to having no gas. So the piston will be dropped. The surroundings will do work on our system. So here, work would be positive. Here we have liquid producing gas. 0 moles of gas, 3 moles of gas. So the piston will be raised, so the system is doing work on the surroundings. We're losing work. All right, so that takes us through the first law of thermodynamics. We've gotten 2 equations, and we've gotten a relationship to convert us between liter atmosphere to joules. And we've also looked at, how can we look at expansion or contraction and interpret work accordingly, according to the system's perspective.